Hi, Algebra 2. In Lesson 2, we're going to continue to focus on our trig functions, but we're going to really focus on the angles of rotation on the coordinate plane. Here we go. The first thing we need to talk about is what is standard position when we're referring to angles. Standard position means that we always have a ray that starts at the origin and goes in the positive x direction, and then we are going to move in a counterclockwise rotation. And we can do that once around, we can do that multiple times around. If we go in a counterclockwise position, it's a positive angle value, and if we go in a clockwise position, it's going to be a negative angle value. Here are a few examples, and these arrows are here to help us. We started on the x-axis. To go 390 degrees, we went all the way around once, that's 360, and then we went 30 more to get to that 390 degrees. 300 degrees, we start here again, and we go counterclockwise, 300 degrees. Negative 150, we start on our x-axis again, and we go backwards clockwise, 150 degrees. In A, I started on my x-axis, and I went counterclockwise, 320 degrees. In B, started on the x-axis, and we went backwards, because it's negative, in the clockwise direction, 110 degrees, so a little over 90. And then in C, 990 degrees. I went around once, that's 360, went around again, that's 720. I needed 270 more degrees to get to 990. Another term that you're going to see in your book are called coterminal angles. You think of co as meaning sharing, right? So these are going to share the same position. It's just that we can write their degrees in different ways. So this example is a 120 degree angle, or we could write it as negative 240 degrees. There's lots of different ways that you could write it. For example, I could do, let's see, 360 plus another 120 would be 480. I could also write that as a 480 degree angle. Here's my 65 degree angle. And another positive angle with the same position would be, I could do 360 plus another 65. I could also write this as a 425 degree angle. With a negative angle, I could start on the x-axis and I could go around this way. Now to find that measurement, well, I know 360 was all the way around, and so I would just subtract, and I would get this to be a 295, negative 295 degree angle. Again, there's lots of options when you're finding coterminal angles, but in this one, I need just one positive and one negative. Well, one positive, I could see that this is the same as a 50 degree angle, and that's because I went 360 all the way around and then 50 more degrees. And a negative angle, well, since I know now that this is the same as a 50 degree angle, I could look at 360 minus 50 would get me a negative 310 degree angle. And I know that when I'm subtracting here, I really do end up with a positive value, but I'm recognizing that I'm going in the negative direction as far as my angles go. So it's a negative 310 degree angle. In your book, when they refer to the reference angle right here, what they're referring to is the smallest value, that acute angle. How could we write that angle? It is always going to be 90 degrees or less because it's an acute angle. So in A here, this one right here is going to be the reference angle. And so I know that straight across there is 180, so I would just subtract, and I would see that this is a 45 degree angle. In B, the reference angle is going to be right here. And again, straight across is 180, and I'm going to subtract off that 105. And so I'm going to see that this is a 75 degree angle. And reference angles, we're always going to write as being positive. Now we're going to look at, once we have our angles drawn, how do we use the trig functions with them? So this table is in your book. It's a good example for us, but I'm going to show you using this example how this works. So first, you draw your angle. And in this case, we don't know what it is. They're just calling it theta. And we drew our angle here. Then we draw a right triangle that goes to the x-axis. Once you have that right triangle drawn with your 90 degrees on the x-axis, we can use the coordinates to figure out some of these lengths. So if this has an x value of 4, that means we went this way to the right 4. So that means the length of that side is 4. And if we went down -5, well, we know the length of that is -5. We're just going to call it -5 for now. Then our hypotenuse right here, we can find using the Pythagorean theorem. So remember, a squared plus b squared equals c squared. C squared is always our hypotenuse. Your book uses r for this a lot when we're doing trig. And so we can fill in the rest of this. 4 squared plus -5 squared is going to equal r squared. So this would be 16 plus 25 equals r squared. When I finish solving this for r, I get the square root of 41. Now, because this is a distance and the hypotenuse, we're always going to just keep the positive value. We don't have to worry about the negative. But what I want you to see is how the Pythagorean theorem right here is the exact same thing as this right here, except instead of saying r squared equals x squared plus y squared, they just solved it for r and did the square root of both sides. So now we have all the lengths of that triangle, and I can start finding the trig ratios here. So the sine of theta, sine is opposite over hypotenuse, and so that's going to be -5 over the square root of 41. The cosine of theta is going to be the adjacent over hypotenuse, so that'd be 4 over the square root of 41. And the tangent of theta is going to be the opposite over adjacent, so it'd be -5 over 4. And I almost forgot, we do need to get in the habit of rationalizing our denominator. We don't want radicals in the denominator. So when you do that, this is what your sine theta would end up being, and this is what your cosine theta would end up being. It really is the exact same value. It's just more grammatically correct for math. Once I had my triangle set up, I used the Pythagorean theorem to find the length of the hypotenuse. So here it is over here. I ended up getting c to be the square root of 117. Remember, your book is going to use r here a lot. But I could break that up and simplify it. 9 times 13 is 117. So 3 times the square root of 13 is the same thing. The opposite angle is going to be, or opposite side is going to be 9. The hypotenuse is going to be 3 times the square root of 13. We are going to rationalize that denominator, multiplying by the square root of 13 over square root of 13. I can simplify here. 3 goes into 3 once, 3 goes into 3 goes into 3 9 times. And this is what I end up with after I've multiplied everything out for the sine of theta. For the cosine, I just need to make sure that I'm using -6 as the adjacent. Don't forget the negative. And then we rationalize the denominator, and this is what we end up with. Tangent's a little bit simpler here. It's just 9 over -6, which simplifies to -3/2. Here's what we end up with for sine, cosine, and tangent. I tried to show my work here, so if you have questions, make sure you look back at that, or make sure you're asking if this stuff isn't quite making sense. Some hints: remember to always write down SOHCAHTOA. That can really help. And then when you're looking for opposite, adjacent, or hypotenuse, it's always going to be referring to our reference angle here. So the opposite was -6, the adjacent is -3, and then the hypotenuse is the length of our ray.